So from watching the video, I was able to get this data that there was a radius, so there was a circle, and a ball bearing came in and collided at the radius of that circle, and we're saying that that radius there is 0.18 meters, that the mass of that ball that hit that circle was 0.04482 kilograms, and it causes to rotate, and it causes it to rotate 3/4 of a circle, and 3/4 of a circle would be 3/4 of 360, which would give you 270 degrees, which is what I said in the video. 3/4 of 2 pi would give you 6 pi over 4, which is the same as 3 pi over 2, which is what it says down here. So that's 270 degrees in radians. And so if I want to work out what the initial momentum of the ball bearing was, I'd go P equals mass times velocity, and the mass was 0.04482 times the initial velocity of 1.705. So that'll give me Pi of the ball bearing. Now, was the platform rotating before the collision? I think you'd see from the video that it wasn't, and so it didn't have any linear or angular momentum beforehand. So this gives me 0.0764 kgms minus 1. Is that what I want? No, I probably don't really want linear momentum, because now we're up in the game, we're going to be looking at angular momentum. And so we're going to go mass times velocity times radius is now going to give me the angular momentum. And so that's really 0.0764, which is the linear momentum, mass times velocity. And if I times it by this radius, 0.18 meters, that should give me the angular momentum that that ball bearing provides to the system. Kg ms minus 1 times meters, which would really make that kg meters squared seconds minus 1. So that is the initial angular momentum, and it's also going to be the same as the final angular momentum the moment after it collides. In the video you see that it does slow down when the ball wasn't dropped from so high, so it didn't have such a high speed. And so is angular momentum really conserved? No, because there is an external torque acting, yet for what we're trying to figure out is probably okay. We're going to make the assumption that there isn't that external torque, and last year would have velocity as distance divided by time, so we're going to have angular velocity equals angular displacement divided by time, and so the angular displacement is going to be 3 pi over 2, and that's going to be divided by the time of 1.11. So if we go 3 pi divided by 2 divided by 1.11, I get an angular velocity of 4.24 radians per second minus 1. Awesome. So I now know the angular velocity omega, and I now know the initial and final momentum of the system. And so I'm going to now use a different equation, L equals I omega, and I want to find out what I is. So I've got 0.01376. I'm looking for I, and it's going to be times by 4.24. Now think to yourself, what is I? Yep, you're right, it is angular momentum. Sorry, it is rotational inertia, but it's of the ball and platform. And so that's something important to try and get your head around. Okay, so how do I find I all by itself? Well, really this is I ball plus I platform is going to be the 0.00324. And so how do I work out the I of the ball? Well, the I of the ball is going to be mr squared. We know the mass from earlier is 0.04482. We know the radius is going to be 0.18. And so what we're going to do is we're going to get this answer, 0.04482 times 0.18 squared, which is 1.45 times 10 to the minus 3. And we're going to take that away from this answer, and that's going to give us iPlatform. So iPlatform is equal to 0.00324 subtract 1.45 times 10 to the minus 3. Which gives me an answer of about 1.787 times 10 to the minus 3 kg meters squared. Awesome.